Okay, everyone. I think we'll make a start because otherwise we're in danger of the session running on late, and I'm aware that we've got tea and dinner and various other things going on. So, well done for getting this far in the course. There's a reason we put all the stats stuff at the end of the course, and that's because, I mean, hopefully you will appreciate now, any of you that have done statistics in the past have probably worked with regression models and things like that. Should be clear now that the types of models we're working with when we're thinking about infectious disease dynamics are typically not regression models, okay? So we can still use standard statistical methods to fit these models to data, but it is much more complicated, okay? So just to manage expectations, what I'm going to be talking about here, so John did a fantastic introduction to some ideas about linking models to data and how you can sometimes simplify the models down or simplify the data down in order to be able to fit the models and generate estimates. What I am going to focus on here are specifically what do we do if we want to fit a fully dynamic transmission model to data, okay? And this is much more challenging. And so what I've tried to do with these lectures is I am not expecting that at the end of these sessions you are all going to be able to run out and fit a large-scale infectious disease model, okay? What I have, because it's difficult, all right, and also because there's not general-purpose software for doing this at the moment. There are bits of general-purpose software that do certain things, but there's not a sort of general piece at the moment. So what I'm hoping to get out of for you to get out of these sessions is to get an idea behind the general concepts, okay? So we'll talk about likelihoods, we'll talk about Bayesian analysis, and we'll talk about Markov chain Monte Carlo, and then we'll talk about particle MCMC tomorrow. So these are effectively ways that we can begin to tackle some of these problems, okay? And in the practical, you get to play around with a few of these ideas, okay? But really the purpose of this is so that when you are reading papers or when you are thinking about your own models, you have some background. So when people talk about Bayesian analysis, you know what it is. If people talk about MCMC, you know what it is. And hopefully you know why it is we have to do it, okay? So that's the kind of idea. So what do I mean by statistical inference? So statistical inference here can be thought of almost as the inverse of simulation, right? So when you did the stochastic simulation lectures and practicals, you took a model, you chose values of the parameters, you plugged them into the model, and then you ran the model to see what happened, right? This is the opposite way around. We can think about data as being a realization of our model, and what we're interested in doing is saying, okay, what parameter values for a model are most likely to give us an output that looks like the data that we observe, okay? So we're trying to estimate parameters. That's effectively what we want to do. And if we can do this, then this is really important because it gives us insights into things like the transmission rate or R0, things like that. But we can also use it to produce predictions and forecasts and do scenario planning, where we are using the data that we observe in order to inform what parameters or what the range of parameters that we want to use in those forecasts are likely to be. And the key thing here is that we want to quantify uncertainty. If any of you have spent any time in the presence of a statistician, you'll understand how much we don't shut up about uncertainty. So let's have a very simple example. Let's look at, this is some data that I've simulated, okay? This is a simple SIR model in a closed population of size 120, okay? And what I've done is I've introduced 20 initial infective individuals at time t0, okay? And then I've just run my model, okay, with some parameters. And hopefully you're all familiar with these curves now. So, you know, we've got the green line here is the infective class. So you see that we get this increase in infection and then it dies out. The red is the susceptibles. And then the R are the removed, okay? So this is a fairly classic SIR model that you will have all seen by now, okay? So if we see some data, and we assume that it comes from a stochastic SIR model that looks a bit like this. Okay, so you've seen this before. So it's got two parameters, beta and gamma, the transmission rate and the recovery rate. What we can do is ask the question, well, what values of beta and gamma produce epidemic curves that are the most consistent with our observations? Okay, that's effectively what we're trying to do when we do statistics. Now, as John introduced really nicely in his lecture this morning, there are various ways that we can approach this question, but the sort of gold standard, if you like, particularly if you come from a classical statistical background, is to use the likelihood function. Okay? And the likelihood function, I'm going to use this notation throughout, okay? So I'm going to use F here to denote a probability distribution, okay? And then hopefully you've seen this notation in the probability lectures. So so Y here corresponds to the data. Theta corresponds to the parameters, okay? And theta here could be a vector. So theta in our case is both beta and gamma. Okay, I'm just using theta so that it's a bit easier than having lots of parameters kicking around. And this is the conditional probability distribution of the data given the parameters, okay? So this is the dependency structure we have. And this function is known as the likelihood function, okay? And the key thing here is that the exact form of the likelihood function depends on both the model and the data, okay? And I'm going to come back to this shortly. Now, this is a very simple example, okay, just to give you an idea of likelihoods, okay? So I want you to imagine that we're not doing infectious diseases anymore. What we have instead are 100 samples from some kind of distribution. So these could be, say, for example, 100 time measurements of something, okay? And I'm going to assume that this is a random sample, so each of these samples is independent of every other sample. And then I'm going to assume that my model, the model that I'm interested in fitting in, is to say that these measurements come from some exponential distribution with some unknown rate, okay? So my task here, so if I draw a histogram of my 100 observations, I get something that looks like this, all right? And so in this scenario, the question is, can I estimate lambda, or can I produce an estimate for lambda which is useful? So in this particular case, because the data are independent of each other, so that means that two individuals don't interact with each other, okay? Then I can write down the likelihood of all 100 observations as just being the product of the probability distributions for each of the 100 observations, okay? And if you remember back to the probability lectures that Andrew did, and also you've seen in the stochastic simulation algorithm, this form here is the probability density function for an exponential, okay? So if they're all exponential, they all have the same shared parameter, then the likelihood is just a product of the density functions evaluated at each of my observations, okay? Now, in the case of estimating parameters, we have observed Y, okay? So the other way of thinking about a likelihood function is that it is some function of the unknown parameters, okay? So the only unknown in here is the lambda, all right? So in a classical statistical framework, so we now say, okay, how do we use the likelihood function to estimate lambda? And one of the ways that we can do that is to try to derive which values of lambda maximize this likelihood, okay? And this is called maximum likelihood estimation, right? So just to illustrate that here, what I've done here is I've plotted, so along the x-axis are different values of lambda, along the y-axis is the likelihood, and what you can see is that if I choose different values of lambda, the likelihood changes, okay? And if I choose a value of lambda down here, okay, that gives me this fitted curve, all right? Then this has a very low likelihood, all right? Doesn't look very much like the data. If I choose something up here, again, now I get a much steeper curve. It still doesn't look like the data. But if I choose something here, where the likelihood is high, then I get a much better fit to the data. Okay? So this is the basic idea behind maximum likelihood estimation. Okay? And because this thing is a function of lambda, in certain circumstances, we can generate an analytical solution because we can differentiate this, or rather we can differentiate the log of this and solve it. But in other circumstances, we might have to use a numerical solver, okay, to find this maximum. So if we take that idea and we go back to our SIR model, well, in an SIR framework, we now have two parameters, right? So we don't have a likelihood function in one dimension. We now have a likelihood function in two dimensions, all right? And in this simulated example, where I observe everything, I can write down a likelihood function for this, okay? It's not simple, okay? Because remember that in a stochastic, in an infectious disease model, one of the key problems is that individuals are not independent anymore, right? So if my data consist of infection times, we know from our model that the infection times depend on the other infection times, right? Or moreover, they depend on how many people are infected, how many people have recovered, okay? So writing the likelihood function down for a model like this is more difficult, but as long as I observe all of the event times and what type of event it is at least theoretically possible to write a likelihood down, okay? I haven't written the form of it here, but I just want you to trust me that in this example I can, okay? So what I've then done here is I've basically taken a range of beta values and a range of gamma, and I've just plotted out the likelihood, okay? So the light areas are the areas of high likelihood, and the dark areas are the areas of low likelihood. And again, what you can see is that we get this likelihood surface. Now, what does this likelihood surface mean? Well, it essentially means that parameters that are in the yellow region here would produce outputs that are more consistent with the observed data than parameters in the dark region. Okay? That makes sense? Yeah? What it does not do, by the way, is it does not guarantee that I'm going to get a good fit to my data, right? It just means that I get a better fit here than I would do over here, all right? That's what. So we can ask the question, what parameters maximize this likelihood? And if I do this, then my maximum likelihood estimator is given by this red dot here, right, which is slap bang in the middle of that yellow region, okay? And I can, if I pull out the estimates, so based on the data that I have, the best estimates for beta and gamma are these ones here, okay, to 3 significant figures.
Why do you say that we're going to get the best fit with the values from the
What's that, sorry?
Why are you assuming that we get a best fit from the yellows?
Because the likelihood is the probability density of the data given the parameters. And the density function, for higher values of the density function, mean you're more likely to observe that. So in that case here, the yellow region corresponds to the areas of higher density. Yeah? So we know that based on the data that we've observed, it is much more likely that the parameters are in this region than they are in this region. Okay? Does that make sense? Yeah. Cool. And in this circumstance, this is not a model where you can derive an analytical solution, so we've numerically estimated this, but we can do this and we can get these estimates. Okay. Now, a couple of things to bear in mind about the likelihood. Firstly, the absolute value of the likelihood is rarely interpretable. Okay? So if I have a likelihood of 100, doesn't mean anything. All right? And that's because if you get more data, your likelihood, the scale of your likelihood will change. Okay? What's important is the relative value. So what we can say is that higher likelihood is better than lower likelihood. All right? But in terms of the absolute value of that likelihood, that is not important. The choice of the likelihood is based on the data and the choice of model, and you will have a different likelihood for different data sets and different models. And maximum likelihood estimates, in fact, even Bayesian estimates, do not guarantee a good fit. Okay? They guarantee an optimal fit based on your model, but if your model is completely misspecified, then the best fit for a rubbish model is still rubbish. Okay? So that's a good thing to bear in mind. The other thing to think about here, and this is where statisticians get obsessed by uncertainty, is that this is a point estimate. Okay? By the way, this black dot here corresponds to the true values. Because this is simulated, okay, I know exactly what the true values are. And you can see that it's not a bad estimate. All right? But the key thing to bear in mind is that there are uncertainties. So within this yellow region, it may be that actually any parameter within that yellow region gives roughly as good a fit as any other parameter. Right? And so we tend to pick a single point as a sort of a simple estimate, but actually there are a range of values which are perfectly consistent with the data. Okay? And so we really want to quantify those uncertainties. And in a classical statistical framework, again, if you've done regression modeling in the past, hopefully you'll be familiar with confidence intervals. But in the classical statistical framework, we would use things like confidence intervals as a way of measuring or quantifying how much uncertainty is associated with a particular estimate. Okay? So in this case, we can derive 95% confidence intervals, and we can get a range of values for these two parameters. Okay? Now, just a little side note, and I will come back to this. I'm sure many of you probably know this already, but confidence intervals, a 95% confidence interval is not a 95% probability that the true value of beta lies between this number and this number. Okay? What it is it's essentially a measure of what would happen if you were to repeat the study over and over and over again. So if we were to do this over and over and over again, 95% of the confidence intervals that we generate would contain the true value. Okay? I make that point purely because when we talk about Bayesian stats, one of the things I think is really good about Bayesian stats is we do actually get probability estimates. Okay? So we will come back to this. But confidence intervals are a little bit difficult to interpret, but it is better to use them to ignore the uncertainty altogether. Yeah?
Just to, the last statement about 95% confidence intervals, I just want to re-say it so it makes sense. You repeat the study 100 times, 95% of the estimates that you get will be within that confidence interval.
Not quite. So again, and when we say repeat the study, we mean if you were to generate new data and refit the model. So it's not that 95% of the estimates would be in the confidence intervals. It would be if you calculated a confidence interval every time you repeated the study, then 95% of those would have the true value inside it. Okay?
That's the first time I've heard it like that.
Yeah, it is a very difficult thing to get your head around, which is another reason why I like Bayesian stats. Okay, but this is called frequentist inference, right? And this is exactly the same idea that you will use if you've done any regression modeling, any maximum likelihood, anything like that. Okay. Now, just very quickly coming back to the point about maximum likelihood estimates don't guarantee a good fit. Just like if you do regression modeling, when you do a regression model, you will check. I noticed somebody mentioned it yesterday, or this morning. We can check things like R squared. We can check the residual plots, right? Those are all things that we use for exactly the same reason, to assess whether our model is reasonable, right? If we fit a poor model to data, we will always get a fit, but the fit is not necessarily good, all right? So I would urge you as well to consider ideas around how you check your model fit. So in this circumstance, what I've done is I've taken those parameter estimates, and then I've simulated from my model a large number of times. Because this is a stochastic model, I get a distribution of outcomes, and I've compared those distributions of outcomes in my three compartments against the data. So the red line here corresponds to the average of those replicates, and the bars correspond to the 95% prediction bounds from those estimates, okay? And the dashed line is the data. So what you can hopefully see here is that those maximum likelihood parameters are giving me a pretty reasonable fit, right? There's nothing that looks weird here, if that makes sense. Yeah? So it's always worth, I raise this because I want to just make the key point that just because you've got the best fit parameters does not mean that your model fits the data well, okay? Now, unlike regression analysis, I mean, as you might be getting the feel in this course, right, these models don't behave nicely in the way that, you know, things like regression do. There are certainly circumstances where doing these simulations naively against the data won't always give you good fits, particularly if you have a stochastic model where you get bimodal outcomes and things like that, then you have to be a little bit more careful. But the basic idea is here, right? You can use simulation in order to assess model fit, okay? If any of you want to see any examples of where this is a bit weird, then we had a paper from a few years ago that does this for Ebola, okay? Everybody happy? Yeah? Cool. So that's a very lightning introduction to maximum likelihood estimates. In the practical later on today, what you'll do is fit the catalytic model that John introduced earlier to some data from Rubella, and we'll use maximum likelihood to do that. Okay, that's not the same model as we've got here, but we can write down a likelihood function, and there's some details in the practical. And then we're going to use a function called optim in our to maximize that likelihood, okay, to generate these estimates. And so this is a numerical optimizer tool. Okay, and there's a few references as well. Does anyone have any questions on that component for a minute? Yeah.
So you highlighted that getting the best fit does not really necessarily mean that you have the best parameters.
So it means you have the best parameters for your model. It does not mean that your model is a good fit to your data.
So what else determines? Because in my mind I thought when you fit your data, your model to the data, it means the model has been able to reproduce the trends.
No.
So which other?
No, it doesn't. So that's the key point. You would like your model to reproduce the trends, and if your model can reproduce those dynamics, then this approach will find you the parameters that mean that it looks like your data. But I mean, one way to think about it, perhaps a simple way to think about it. Imagine I've got some data that look like a curve, but I choose a model that's a straight line. I will get estimates of the slope and gradient of that line, but it won't go through my data points because my data points are a curve and my model is a line. It's the same idea here. We would start with a model and we would hope that that model is able to reproduce the outcome, but it's not necessarily the case. So if your model is misspecified in some way, then it may be that you don't get a good fit to your data, right? Because your model is misspecified, yeah? So for these simple time series data, that probably happens less, but when you start getting up to kind of meta-population, spatial models, more complex models, then it gets actually very hard to assess whether your model looks like your data. But the usual way of doing it is to try to produce predictions of your data points and compare them to the observed data and see if they're consistent or not. Okay? It's the same idea that you'd use in regression, but in regression you can do residual analysis or things like that, whereas these models it's harder because the models are more complex. Yeah, does that make sense? Cool. All right. So this initial, oh, sorry.
So I want to ask the 95% confidence interval you explained, is it the same as the credible interval?
It's not the same as the credible interval, and I will come on to the credible interval in the next set of slides. Okay. Sorry, this lecture has been split into two, but it is essentially one big lecture. So what I'm going to do now is talk about Bayesian statistics. Okay? Does anyone have any last questions, or are we all right to go on? Okay. So, okay. So, there's a brief introduction to maximum likelihood. Okay. Now I want to introduce you to a slightly different way of thinking about fitting models to data. And that is to use something known as Bayesian inference or Bayesian modeling. Okay? I'm horribly biased because I'm a Bayesian statistician, so I really like this. But one of the reasons why we are showing you both of these approaches is because, particularly when you start to get up to these more complex models where you have a lot of missing information and other things like that, the Bayesian, I mean, I think there's lots of reasons why I prefer the Bayesian method, but just even from a practical perspective, often this can work better. Or in some cases, you can solve problems with this method that you can't solve with maximum likelihood very easily. Okay, so there's lots of reasons, and this is becoming an approach which is used a lot more in the infectious disease literature. Okay, so I think it's important to introduce you to these ideas so that you have some have been introduced to these, because if you read papers, you will see people using Bayesian modeling. Okay, so how is Bayesian modeling different to classical statistical modeling? So the way to think about it is in terms of the way that we think about the parameters. Okay, so in the classical approach that I've just showed you, what we do is we consider that the parameters are fixed. There is some true value, okay, that exists out there, and if we had enough data, we would be able to estimate that exactly. Okay. Now, the Bayesian method makes the same assumption, but with one key difference, which is that in the Bayesian method, you assume that you have some uncertainty about your knowledge about what the parameters could be, right? So you acknowledge that, oh, okay, I might know something about the parameters, but I'm not really sure what I know, right? Or I am sure about what I know if I have an informative distribution, okay? So effectively, from a practical perspective, the Bayesian framework treats the parameters themselves as if they are random variables, okay? So we're used to thinking about the outcome as being a random variable. In the Bayesian framework, we also treat the parameters as being a random variable, okay? And what this means is that we can model those parameters as having a probability distribution. And if we do that, then we can use all of the benefits of probability distributions. So we can generate 95% probabilities that the parameter lies in a particular range, or we can generate, you know, what is the probability that R naught is bigger than 1, right? That's a question that you can't answer if you're not prepared to treat a parameter as a probability distribution. So this is the basic idea. And the concept, so Bayesian statistics is named after this guy. This is Thomas Bayes. He was alive in the 1700s. And what he came up with, so he had a paper that was published posthumously by a mate of his, but it was basically just a paper looking at the relationship between conditional probabilities. Okay, so in Andrew's probability lectures, we introduced the idea of conditional probabilities, right? So this is the probability of an event A given an event B, okay? And what Bayes' theorem basically does is it just says, well, if I'm interested in this thing on the left, I can write this as the probability of the event B given A times the probability that the event A happens divided by the probability that B happens, okay? It is just quite a simple, I mean, it can be derived just from very basic probability rules, okay? Now, you might think, well, why is this useful? And hopefully I will try to elaborate why this is useful. So,
Before you go on,
yeah.
do people popularly use the frequentist approach now?
So I would say in infectious disease modeling, I personally see more Bayesian stuff being used. If you're thinking about regression models, that is, a lot of that is still frequentist. But again, people are using Bayesian models a lot in that circumstance as well. So yeah, frequentist inference is much, much more widespread because historically that's what we've been taught. That's what you tend to get taught if you've done any course on regression, you will have done that. Bayesian modeling is becoming more common and more popular very fast. So if you've gone back 30 years, Bayes is a niche thing. Now people are using it everywhere.
So the logistic regression is frequentist.
No, logistic regression you can fit in a Bayesian way. if you want to. The only difference between, so the difference is not the model, the difference is how you estimate the parameters and how you treat the parameters. So you can do Bayesian logistic regression, and in fact I do that a lot in my other role as working in diabetes research. We do a lot of this. So, yeah. Okay, so how does Bayes' theorem apply to our idea of how to estimate parameters of a model? Well, what it comes down to is this relationship here. Okay, so this is Bayes' theorem, but rather than A and B, I've substituted in the parameters and the data. Okay, and I'm going to go through this line by line. So, the key thing that we're trying to do is we're trying to use data to learn about the parameters. Okay? So this thing on the left-hand side here is the probability distribution of the parameters given the data. Okay? So if I have some information in the data, how does that impact my uncertainty about the parameters? Okay? And this thing on the left here is called the posterior distribution. And if you read any Bayesian model, they will talk about the posterior distribution because this is the thing that we are trying to estimate, okay? Because this is telling us how our observed data impact on our estimates of the parameters. Now, if we go to the right-hand side here, this thing, well, you've hopefully seen that before, right? This is the likelihood function. It is the distribution of the data given the parameters, okay? So that is something that, this is, if you like, how we encapsulate the information in the data, which is, again, dependent on our model. Then we have this thing here, which is the distribution of the parameters. And notice that there's no dependency on the data there at all, okay? And this thing is called the prior distribution. And what this represents is what our prior belief in the parameters is before I've seen any data. Okay? Now, I should clarify here, this is our belief in the parameters before I've seen the specific data that I'm fitting the model to. However, if I have historical data or information from the literature or other things, I can use that if I want to derive some kind of prior belief. Okay? So I can use data to inform the prior, I just can't use the data that I'm fitting my model to. All right? And I'll come back to this a little. This thing on the denominator here is what is called the marginal likelihood. Now, I don't want you to worry about this. What I just want you to understand is that this is a function of the data, and we observe the data. So f of y is a function of a bunch of things that we observe. Okay? The only things we don't know are the parameters. Okay? So this thing here is actually a constant. Okay? One of the challenges we've had with Bayesian stats, and one of the reasons why it took quite a long time to be kind of practically useful, is the fact that if we write this out mathematically, this constant is equal to the integral of the numerator over all possible values of the parameters. Okay? Now, in some very simple models, we can calculate this integral. In many, many other models, we can't. All right? Or at least we can't write down a functional form for it. Okay? So we don't actually have a way, if we don't have a way of calculating this, then we can't write down the posterior distribution completely. And that means that we can't really use it very easily. Okay? And this has been the major stumbling block. Okay? And I will talk to you, in the next lecture, we will talk about Markov chain Monte Carlo, which is a technique that we use to estimate posterior distributions without having to calculate this thing. All right? But all I will say is that we tend to have to jump through hoops to avoid having to calculate this thing. Okay? And that's one of the reasons why Bayesian methods took a long time, because you need a computer to do it. Okay? Unless you've got a very simple model where you can work out this analytically, you tend to need a computer. So it's only really probably been in the last 30 or 40 years where the availability of computing power has got to the point where we can routinely use these models. Okay? Right. So what we tend to do when we're thinking about likelihoods is we tend to write the posterior like this. So this symbol here means proportional to, okay? So the posterior is proportional to the likelihood times the prior, okay? So there's some constant multiplied by the likelihood. Okay? So sometimes you'll see that notation. Okay, so let's go back to our SIR example, okay? So how would we apply a Bayesian, how would we estimate the parameters for this model in a Bayesian framework, okay? So what we first think about is we're going to write down the form of our posterior distribution, all right? So remember, we have two unknown parameters, beta and gamma. So what I'm interested in deriving is the posterior distribution of beta and gamma given the data, yeah? And I can write that as being proportional to the likelihood multiplied by the prior, okay? So the likelihood is exactly the same as it would be in classical frequentist maximum likelihood, okay? But what we do need is a prior distribution for these two parameters, okay? And if we do this, if we specify this prior distribution, then we can derive the we can estimate the posterior distribution. So let's think about how to derive this prior. So I will talk about priors in a little bit more detail in a few slides' time. For the time being, I just want to introduce the idea that your prior distribution has to be a probability distribution, okay? But it has to be a probability distribution which is sensible for the parameters that you have, okay? So both of these parameters, beta and gamma, are both rates, right? And so as such, they can't be negative, yeah? So at the bare minimum, I need, not only are they must be positive, but also they must be continuous, right? These are not discrete parameters, right? They're continuous. So I need some kind of prior distribution which is both positive and continuous, okay? At a bare minimum, all right? Because that ensures that my parameters are correctly specified, okay? At least epidemiologically. Does that make sense? Everybody happy with that? Yeah? Okay, cool. The other thing that people often tend to do, and I'm going to do it here, is I'm going to assume that these two things are what we call a priori independent, okay? So I'm going to say in the absence of any data, beta and gamma are not correlated with each other, okay? The value of beta doesn't depend on the value of gamma. You don't have to do this. You can write this joint distribution as beta given gamma times gamma. You can introduce structure if you want to, and in fact we do this a lot in what's called Bayesian hierarchical modeling. But in this circumstance, I'm just going to assume that they're independent. And if they're independent, then you can get the joint distribution by multiplying the marginal distributions, okay? So I'm going to write this as a distribution for beta multiplied by a distribution for gamma, okay? Now, for the sake of just illustrating how this works, I am going to choose two very simple distributions here, okay? In practice, you would want to think about what your prior distribution is carefully in advance, all right? But I am going to just say that beta has a uniform distribution between 0 and 0.03, and that gamma has a uniform distribution between 0 and 0.3, okay? This is purely so that I can show you what the priors and the posteriors look like on the same graph, okay? But notice that both of these things are continuous and bounded below by 0, so they're valid priors, okay? In practice, if I was doing this, I would make these priors much flatter. I probably wouldn't put a hard bound on the end here, okay? But I'm doing that purely to just illustrate. So if I do this, then I can work out the probability density function for each of these priors, and because they're uniform, that's constant, okay? So don't worry too much about what these numbers are here, but these are basically just constant values, okay? Because in a uniform distribution, you're equally likely to take any value in that range, okay? So the probability density is constant. Okay, but I've now specified the priors, and now I have everything I need on the right-hand side here to estimate the posterior distribution, all right? Now, I can't, in this circumstance, estimate this posterior distribution analytically, So what I've done here is I've used a technique called Markov chain Monte Carlo, and I've estimated this numerically, okay? And I'm not going to dwell on how to do this. That will be after the tea break, okay? We'll talk about MCMC. But essentially what I've done here is I've plotted out beta along the x-axis, gamma along the y-axis, and the ranges are the ranges of my prior distribution, okay? So you know I said set those uniform priors? That corresponds to this bar, okay? That's why I chose quite narrow ranges, right? And then what I've plotted in the middle here is, again, an estimate of the posterior density, okay? And this has the same interpretation as the likelihood, right? Higher values here mean that you've got a higher probability density, yeah? So remember you get those probabilities, like a gamma distribution where you get a peak, or a normal distribution where you get a peak, right? So this is the peak, and then as the colors fade out to dark blue, you have a lower density, all right? Now, the eagle-eyed among you might say, well, that looks kind of similar to the likelihood, right? And in fact, it is in this case because we've got uniform priors. Okay? But before I get onto that, what I will do is to say, okay, this is a joint distribution, okay? How do we use this in practice? Well, the way that we would usually present the results of a Bayesian model is by using what's called the marginal distributions, okay? And all the marginal distribution is, if you look at this plot here, is we can collapse a two-dimensional distribution into a single-dimensional distribution, okay? And mathematically, we do that by integrating across the other parameter, okay? I don't want you to worry about this. Because we estimate this numerically, this actually becomes as simple. What we end up with is random samples for beta and random samples of gamma. And if we just take the betas and ignore the gammas, and we plot them out, we get the marginal. And similarly for gamma, okay? So we can do this very easily numerically, but this is the sort of formal definition, okay? Similarly, if I want the marginal distribution for gamma, I can integrate out the joint distribution over beta, okay? So you can think about this as like collapsing either that way or that way, okay? And if I do this, so what I've plotted on the top here is the marginal distribution for beta, and that's the solid line. And then I've overlaid on top of that the prior distribution, all right? Remember, we had a prior distribution that was uniform, so that dotted line here is the prior distribution, okay? And so in advance of seeing the data, I'm saying, well, beta can be anywhere between 0 and 0.003, and every one of those values is equally likely, okay? But once I've shown it the data, notice my posterior distribution does not look like a uniform anymore. In fact, my posterior distribution is very, very peaked around this point here, yeah? And furthermore, it says that you're very, very unlikely that the true value is outside of this range here, right? Yeah? Is everybody happy with probability distribution? So the area under the probability distribution gives you the probability. So I can say the probability that beta lies between here and here is very high, yeah? Because most of the area of the curve is within this bound. Okay? So the posterior distribution, I can use that in various ways. The other way I can use it is if I want a point estimate, right? So if I want a point estimate for beta, well, how do I do that? Anyone have any ideas how I could derive a point estimate from a distribution? Go on. Go on. Say it. No? Yeah?
If you transpose that graph down, what's the other graph that is the point of intersection where you're right? There's a line there. So what's the point of intersection?
Do you mean, so what you're saying you can choose a point, what, the point where that this is biggest?
If you transpose that one on this,
What, this one here?
yes.
So this is the, this is the marginal distribution for gamma, and I've just flipped this around. But what I was thinking about was what sort of summary measure of a distribution would you use to summarize it. If you've got a normal distribution, you might think about means, yeah, and variance, standard deviation, median, mode, right? So in fact, because it's a probability distribution, we can use any of those measures that we like, right? So if I was choosing the posterior mode, then that would be the area it maximizes here. If I was choosing the posterior mean, well, that would be very similar in this case, and the median would be very similar again, because this is fairly symmetric, okay? But any of those measures would be fine, right? So, and again, we can do a similar thing with the gamma, okay? And again, you can see that we learn a lot from the gamma. So we have this uniform distribution to begin with. Once we show it the data, we've learned a lot, right? And so once we've got these distributions, so what I've plotted out here is what's called the, well, I've called it the 95% credible interval. It's actually the, no, this is the credible interval, it's fine. So this is a region within which we have a 95% probability that our true value lies, okay? And this is what's known as a credible interval. And I can generate this from the outputs of my model. So I can generate a point estimate, which I've done through the posterior mean, okay? So I get a posterior mean estimate as a point estimate. I get an estimate of the standard deviation if I want it. But I can also derive things like the credible interval. So in this circumstance, what this is saying is, based on our prior distribution and based on our data, there is a 95% probability that the true value of beta lies between 0.00078 and 0.0013. Okay?
That's the credible interval.
That is the credible interval.
That is the definition of 95% confidence interval that I've always known.
Yes, but it's not, is the key point, yeah. So yes, it is absolutely how a lot of people interpret confidence intervals, but in the Bayesian case, it's actually true, all right? And similarly for gamma, okay, we get point estimates and we get these credible intervals. Now, we can compare these to our maximum likelihood estimates, and what you can hopefully see here is there's basically no difference, right? The point estimates are very similar to the maximum likelihood estimates, and in fact, in this case, the confidence intervals, the 95% confidence intervals, are very similar to the 95% credible intervals, okay? Now, the reason for that is because these prior distributions are flat, right? And what that means is that essentially, the credible intervals are derived from the likelihood, okay? And often, particularly if you've got some, kind of quite well-behaved data, in some circumstances, they are always identical. If you do Gaussian regression, they're always identical, as long as you have a flat prior for everything. In this circumstances, they're very similar, okay? And that's because there's a lot of information in the data, and we're using flat priors, or uniform priors, okay? However, just because they are the same values does not mean the interpretation is the same, all right? James Wood hates it when I say that. Okay, so is everybody happy with that as an idea? Yeah? So all we're doing with a Bayesian model is we're estimating a distribution, and then we're using that distribution to tell us about uncertainty and about parameters. Now, in terms of interpreting what that distribution is, the way to think about it, the way I like to think about it, is you can view the posterior distribution as reflecting the degree to which our prior belief changes once we have some data, yeah? Because we take our prior, we multiply it by the likelihood, and we get a posterior, okay? So the posterior distribution is a balance between our prior belief and our data, okay? And in fact, this idea is what underpins the whole concept of Bayesian learning, where you can teach machine learning algorithms effectively can get better by taking some prior, showing it some data, updating its posterior, then showing it some, and then using that posterior as a prior, showing it some more data, okay? And this idea is how we as humans learn as well, right? If you're a baby and you see a fire, you wander over to it because your prior belief is that this is fine, and then you put your hand in it, and then you very quickly learn, right? Not to touch hot things, right? This is essentially the idea. We're just, and we can use this kind of in lots and lots of different ways. Now, I want to digress a little bit about prior distributions because, again, historically, I speak to a lot of statisticians who are not Bayesians, and they basically say, well, I don't need to use Bayesian statistics because I don't have a prior, right? My argument to you, or rather, so my first argument to you is that there's lots of reasons to use a Bayesian. So if you really don't have a prior distribution, then that's fine as well, because you can just make your prior distribution flat. Yeah? You make it uniform over a very large range, and effectively that means that your prior will have very little weight, and your posterior will look very much like the likelihood. Okay? So if you're worried about priors, that you don't just have to use Bayesian methods if you have an informative prior. Okay? That's not a problem. But one of the kind of I think that this is a bit more, is not really as prevalent as it used to be, but certainly back in the 30s and 40s when people like R.A. Fisher were around, they used to use this argument that Bayesian statistics is nonsense because your prior distribution is subjective, right? I might have a different prior distribution to you, or a different prior distribution to Andrew, or to you, whatever. Everybody has a different subjective prior. And of course, if you have a different prior distribution, you get a slightly different posterior, okay? And Fisher in particular hated this, right? And used it basically to kind of stifle Bayesian statistics for many, many years. I think that we're more nuanced about this now, right? We do have to be careful. So if you use a very informative prior, so if you say, for example, I'm really, really sure that my parameter is in this small range, okay, then I think, as Isaac pointed out yesterday, it may be that your posterior is quite sensitive to your choice of prior, and that means that any inference you make has to be justified by that prior, okay? So moreover, if that prior is poor, if it's not very well thought out, then you can get misleading results. That is absolutely true, okay? So you do have to be very careful if you use informative priors to justify them, and it is usually safer to use flatter priors. So quite often what people do nowadays is they use what's called weakly informative priors. So you might have a prior distribution that basically puts your parameter in the right order of magnitude, but that is not too specific about what the value could be. So if you were thinking about something like R0, for example, if you knew you had a respiratory disease with R0, you could put a flat distribution and say, well, it could take any number from 0 to 1,000,000. But that's probably not true. It's probably better to put some distribution. You know it's not going to be 100, right? Probably know it's not going to be 50. May not even be 20. So you don't have to be too specific, but you can focus things down on a range which is biologically plausible. That's one way you can do it. But just on this point about subjectivity, one thing I will state to all of you is that the likelihood is also subjective, right? How you choose your model is entirely subjective. Everything about statistical modeling is subjective, okay? The idea that your likelihood is objective because it's a function of the data is not true, because it is a function of the data and the model. And for most data sets that I come across, I can think of 20 or 30 models that are all biologically plausible that I could choose to fit, okay? And each one of them, if I fit a different model, is going to give me a slightly different answer, all right? So just bear in mind that everything is subjective, and you have to just treat priors with as much caution as you have to treat likelihoods, okay, and models. There are circumstances, however, and some Bayesians, particularly in the area of subjective Bayes, will argue that we do have a lot of information about many of these parameters a priori if we just think about it hard enough, okay? And that it is sensible to build that in. And generally what will happen is if there is a lot of information in the data relative to the prior, then the posterior will just be driven by the data, and it's not much of an issue. If it's the other way around, then you might have to be a little bit more careful about thinking about justifying the prior. Isaac, sorry, you had a point.
Thank you very much. Yeah, I also just wanted to add that we can as well do statistics analysis with the power prior mechanism, where if you have informative prior, you have so much data, you believe the plausibility of what data you have and it is biologically correct. And you want to see whether adding just 0% of that will influence the 25%, 50%, and 100%. So you can see how the priors are actually influencing the estimates. When you don't put anything, when you add anything, you add probably 100% of it. So then you can check how sensitive are your estimates are. Or probably you can use the modified priors for the regression. Those parameters themselves you can actually, come up with. So I tend to tell colleagues that I think we have matured as Bayesian statisticians. We can always find a way of demonstrating bigger in our methodology because approaches that are valid.
Yeah, absolutely. That's a fantastic point. Yeah, yeah. But one thing I will just add to that is that it also doesn't necessarily invalidate your results if your model is sensitive to your prior. But what it means is that you just have to be very, very sure that your prior is valid, right? That it's a reasonable prior. And you have to be open when you write this, that this is sensitive to the prior. Okay. So vague priors are usually safer. I've used vague here to mean flat priors, okay? But you can do the sensitivity analysis. That's fantastic. Now, a couple of questions. Why should we care about Bayesian methods? And I'm going to avoid a massive full-on philosophical debate here. I'm just going to raise a few arguments. The first one I've already raised, which is that I would argue, once you wrap your head around Bayesian stats, that how we treat probability is much more natural than how we treat probability in a classical framework. Okay? Rubin, in this paper from 1984, says that consumers of statistical answers almost uniformly interpret them Bayesianly. And what he means from that is exactly what you were saying over there, is that we get taught 95% confidence intervals as if they are probability statements about the parameters, and they are not. But probability statements about the parameters are good things to have. They're neat, they make sense, right? And this framework gives you that. Now, secondly, the use of prior distributions, and by extension, hierarchical structures, which we use a lot for things like missing data problems, spatiotemporal problems, and various other things, enable us to fit models that are very difficult to fit using classical methods, okay? And it also means, as well, that you can also fit models where some of the parameters are what's called unidentifiable. So you might not have enough data to estimate a particular parameter, which your model depends on. Now, the Bayesian approach to that is you put a prior distribution on the parameter you can't estimate, and then you can estimate the other parameters conditional on that prior. Okay? So it is a mechanism for being able to get around unidentifiability. What you won't do is learn anything more about the unidentifiable parameters, but you will be able to say something about the other parameters conditional on those priors. So there are kind of useful things that one can do, which are, they're usually useful in niche circumstances, but they're still useful. And then one more point is that it is very straightforward to propagate uncertainty through to predictions. Okay? So when we're predicting into the future, if we were doing this in a classical way, we would fix the parameters, we would simulate our model into the future, and we would see what the uncertainty was, right? But that uncertainty is only a function of the model, because we are fixing the parameters to be a single value. Okay? So if you like, I would argue that you're getting a false representation of what the true uncertainty is regarding your predictions, because you are ignoring the uncertainty in the parameters. Now, there are simulation ways that you can do this with maximum likelihood, where you simulate, essentially it's like an imputation type approach, right? You simulate various versions of your parameters and then you propagate those forward. But in the Bayesian framework, it comes out naturally. Because you've got a distribution, you can take a random sample from that posterior distribution and then use that to do a simulation, and then take another random sample from your posterior distribution, plug that into your model, do a simulation. And so what you end up with at the end is prediction intervals that incorporate both the uncertainty in your stochastic model, but also the uncertainty in your parameters. And it's very easy to do this for much, much more complicated models.
Sorry?
Yes?
Does it have any effect on the quality of data, for instance? Like, you know that the data you are using is not that much of good quality, but you are adding a prior information to the data. Does it in any way have an effect on the quality of the data?
So it doesn't impact the quality of the data, because the data aren't dependent on the model, right? But in terms of the quality of the inference, then you know, if your data, well, it depends what you mean by data being poor. If your data are poor because you don't have many data points, then that will get reflected in a large uncertainty. But that will get reflected in a large uncertainty whether you do maximum likelihood or Bayesian analysis, because that's a function of how much data you've got and a function of how much information is in the likelihood. If your data are poor because they're biased, then that is a different question, right? Because that's something, so then what you would have to do is have something in your model that accounts for the bias, okay? And again, that is framework agnostic. So if you have a bias, you would have the same problem in a Bayesian model than you would have in a classical frequentist model. But you would have to probably deal with that within the model itself. In terms of prior distributions, of course, where if you've got a low number of samples and you have a fairly informative prior, then as long as you can justify that prior, then you will get potentially less uncertainty in your Bayesian credible intervals than you will do if you were to do confidence intervals. Because confidence intervals, you can almost think, you could think about them as being related to the idea that if you did a Bayesian model with completely flat priors, but obviously if you make your priors more informative, then your uncertainty is probably going to be less. The question about whether that's more robust or not depends on how good your prior is. Yeah. Okay, so this is just a very brief table about the key differences between the two approaches. And I've basically said all of this, so I won't go through it again. But it's there if anyone wants it. If anyone wants to, I put this in here just because I've quoted it. I'm not expecting any of you to read it because it's from the 1700s and it's not fair. You know, if any of you really want to get into Bayesian statistics at all and you want a core textbook, then this one is the one you want, right? Andrew Gelman's textbook with Donald Rubin, John Carlin, and Hal Stern. So this is the Bible of Bayesian stats. It is not an introductory, I mean, it's not super, super technical, but it's also not a very simple introduction to Bayesian stats. The book I would recommend as an introduction to Bayesian stats is Statistical Rethinking by a guy called Richard McElraith, and I think we're putting some links to that. Yeah, we got that. That is a very high level. He uses a lot of analogies to kind of explain the way that you can use Bayesian analysis to think about different things, okay? I should have added it in here, but I haven't, okay? But this is the Bible in terms of the technical stuff, all right? And there's an updated version of this. There's a 2013, I think, possibly a 2017, something like that. Okay, that's the end of those two lectures. I appreciate we're just running into coffee by a couple of minutes. Does anyone have any questions on that? Yeah.
So, do we also compute the p-values in a Bayesian?
Not in a Bayesian framework. We don't use p-values.
So we use the credible.
You would tend to use the credible intervals. You can also, so one thing you can do is to ask probabilistic questions about the parameters. So you can, a p-value basically says if the parameters if the true value is 0, what would I expect to see? I'd argue that's not really what we want to be asking. What we want to be, like, if I had R0 that I was estimating, I'd want to say, well, if R0, what's the probability R0 is bigger than 1, right?
No. I'm not talking about the infections. For example, you say you can fit a logistic regression model in a Bayesian way, and then we have our odds ratio, and then we have the credible interval.
Yep.
So in the classic way, we could maybe use the p-values to say whether there is statistical significance or not. So I was wondering if it works the same way in a Bayesian.
Generally not. So the p-value, yeah, so you can use credible intervals, which give you essentially the same information as a p-value would give you, right? You don't ask a p-value type question exactly because of the way the p-value is specified. What you would tend to do in a Bayesian model instead is to say, okay, rather than saying, is this odds ratio big? So let's say an odds ratio. What you would do is you would say, okay, my p-value is relative to a null hypothesis that my odds ratio is 1. Yeah, and you look for evidence against that being true. In a Bayesian analysis, you get an entire distribution for that odds ratio. So you can ask different questions. You can say, what is the probability that that odds ratio is bigger than 1? Or what is the probability that odds ratio is less than 1? Or you can define a very small region around the odds ratio of 1, which we would call the region of practical equivalence. And you can say, what's the probability that my true value is in that region, where essentially I'm saying there's no difference, I don't care about it. So you can ask lots of questions, and in fact you can do non-inferiority stuff, you can do comparative stuff, you can do equivalence measures, but they are not exactly p-values. But I would argue, sorry, one more thing, I really don't like p-values. I think there are lots and lots of problems with them, and there's a lot of literature now coming out to basically say that there's a lot of problems with them. So I would always use confidence intervals anyway myself, rather than p-values, but even then, you know, there's different things. So you can answer the same questions, but in a different way, I guess, is what I'm saying. Okay. So I'm aware that we're sort of running over a little bit. We have coffee. Matono said to tell you all that if you want coffee, please take your tags, because there's 2 groups, and they'll only give you coffee if you're on this group. So if we take, was it 15 minutes for coffee?
We'll start at 20 to 5.
Okay.
Sharp.
Yeah.
But then you get to priority.
Oh, sorry, 2 seconds. Let me just get this one up, and then it's ready to go. Yes.
Good. I'm really interested in Bayesian statistics approach, and I'm a PhD student in malaria modeling.
Yep.
And then for the first subjective, I want to look at the impact, the retrospective impact of SMC, seasonal malaria prevention in
Okay.
Benin. And I'm still looking at what is the method I can use. Like, I really want to use Bayesian approach. So what I've suggested is a general linear base effect model. I've suggested, but
So random effects model.
yes.
Yeah.
So I don't know if kind of you have other suggestions.
Well, so what I would say about a random effects model is that that is exactly the area where Bayesian stats is really good. Because a random, so again, it's sort of in a random effects model, in a classical framework, I'll turn this off a second. Right, so we're running a bit behind schedule, so this is going to eat into the practical session a bit, but I will try to get through this as quickly as I can. So, what I want... I'm sorry, this is really loud. Probably too loud. Okay, right. So, what I did in the last... So, what we've covered at the moment is the idea of maximum likelihood estimation and Bayesian estimation, okay? So, what I want to talk to you about briefly before the practical is how we go around estimating posterior distributions, okay? And this is really the thing that makes Bayesian analysis, I think people think it's harder, and I think it's harder typically because we have to estimate distributions instead of just estimating a single point. I would argue that once you get comfortable with doing this, you can do a lot more with the distribution, but it is not straightforward, okay? And so, because we can't write down these analytical distributions except in very, very simple cases, we need some kind of numerical algorithm that enables us to estimate the distribution, okay? And there are lots of these, but the one I'm going to focus on for the purposes of this course is one called Markov chain Monte Carlo, which many of you may have heard of before. So we're going to go through what Markov chain Monte Carlo does, just really to give you an idea. You are not going to have to code up your own Markov chain Monte Carlo algorithms, you'll be pleased to know, okay? But this is just to give you an idea how to do it. So, what is the problem? The problem is, because we can't write down this analytical form, it's very difficult to work with this. So, what we're going to do instead is to generate an empirical estimate of this distribution by random sampling, okay? So what we're going to do is we're going to take lots and lots of random samples from our posterior distribution, and then we're going to plot them out, right? And that's going to give us an estimate of what that distribution looks like. And also, if we take a large number of random samples and we take their sample mean, then we get an estimate of the mean of the distribution. If we take a large number of samples and we take the standard deviation, we get an estimate of the standard deviation. Yeah, does that make sense? So this is basically the idea, okay? And so this general concept of estimating distributions or estimating sort of summary measures of distributions using random sampling is what's sort of colloquially called Monte Carlo estimation, right? And I'm sure that many of you will have heard of Monte Carlo estimation in one way or another, okay? And I would say that Monte Carlo estimation is a very general estimation. You can use it to estimate any integral, for example, even if the integral is analytically intractable. And this all came out of work that was done in Los Alamos in the 1940s. In fact, it came out of the Manhattan Project, a lot of these numerical techniques. So at least something positive came out of them, I guess. Okay, just to set the scene, a little bit of revision on probability distributions. I want to consider that we have some random variable x, okay? And that comes from a probability distribution with a probability density function given by f of x. Yeah, everyone happy with that? Seen this before? Now, just a couple of terminology, expected values, right? Mathematically, the expected value of x is defined as the integral over all possible values of x times the density function, okay? In practice, the expectation is the mean of that distribution, all right? So whenever we talk about expectations, we mean means, okay? Mathematically, this is how we can calculate the mean. And essentially, if you want a sort of conceptual idea of what the mean is, you can think about the mean as being a weighted average, right? So I take every possible value of x and I weight it by the probability density function. And if I do this, if I take the limit and I do this across the whole space, then I end up with an integral, okay? And so for some distributions, like if I've got a normal distribution, if x is normally distributed, okay, then this integral would look like this, right? So the range of x, if I have a normally distributed random variable, is minus infinity to plus infinity, okay? And then I have x times the density function. And this is the probability density function for a normal distribution with a mean mu and a variance of sigma, yeah? And I am not going to sit and do this, but if you do this integral, you end up with mu, right? That's where it comes from originally. A slightly easier example is the expected value of an exponential distribution. It's exactly the same equation. Okay, it's the integral, but now if I have an exponential random variable, that's bounded below by 0, right? Exponential random variables have to be positive. So this is the integral from 0 to infinity of x times the density function for x, right? Which is this form that we saw, or we've seen plenty of times. This is a much easier integral to do, and if you do this integral, you get 1 over lambda, okay? So this is all an expectation is, right? And I will come back to why I'm focusing on expectations shortly. Okay? Well, one thing about expectations is that if you want to estimate the expected value of a set of data, right, or of a random variable, what we would typically do is go out and collect a bunch of data and then calculate the sample mean, right? If I want to know what the average height of a population is, I can take a large random sample from that population, measure everyone's heights, and then take the sample mean, okay? So that's a very easy way of estimating this, okay? So sample means are really good estimators, okay, because you can show that they are both unbiased and consistent, right? So unbiased means if I were to take a bunch of random samples over and over and over again and calculate the sample mean each time, if I take the average of those sample means, it will be the true value. And consistency means that as my sample size gets larger, my uncertainty around my estimate gets smaller, okay? So this is why we use sample means all the time. And actually, sample means are completely independent of the distribution, so they're really good estimators, okay? And this underpins the idea of Monte Carlo simulation, okay? So the key thing is, as long as you can produce random samples from some distribution, then you can estimate the mean of that distribution as the sample mean of those random samples, okay? Now, of course, if I was collecting data, I wouldn't be generating random samples, right? I would just be assuming that every person I select at random is a random sample from the distribution of heights of a population. But we can apply the same idea to any probability distribution. So we can do this in a computer as long as we know what f of x is, or rather, as long as we can sample from f of x, then I don't even need to know the analytical mean. I can just take a really large number of random samples from my distribution, and if I calculate the sample mean of those, it's going to be a really good estimate of the mean of that distribution, okay? And this is the basic idea, this is the essence of what we call Monte Carlo estimation. Okay, so here's an example from an exponential distribution. So if we go, so in this case, what I've done is I've drawn random samples from an exponential distribution with a mean of 100. Okay, so in this example, I know what the true value is because I'm using that to simulate. And what I've done is I've firstly taken a sample of size 5 and calculated the sample mean, right? And then I've done that 1,000 times, and then I've plotted out the average of those and the uncertainty bounds, and then I've repeated that for different sample sizes, going from close to 0 up to 5,000. All right? And what you can see is that if I take the average of those Monte Carlo estimates, then they lie absolutely bang on the true value. Okay, this is the unbiasedness property. Yeah? But what you will notice is the uncertainty is big. So if I take a small number of random samples, then there's a high probability I could be quite a long way away from the true answer. Okay? But as I increase the sample size, this averages out and gets closer to the true value, okay? And if I were to take the limit of this up to an infinite number of samples, it will just converge on the true value, okay? So this is a property. Monte Carlo estimation is always unbiased, but if you have a large number of samples, you have a small variance, and a small number of samples gives you a large variance, okay? So when we do Monte Carlo estimation, what we're doing is trying to balance how many samples do I need to take in order to get a reasonably good estimate of the thing I'm trying to estimate? Okay. Now, this is just a quick aside because we're going to come back to this later on. This is just a slide with something known as the law of the unconscious statistician. Okay? All this says, all right, is that when I'm calculating the expected value of x, that's the integral of x times f of x, yeah? Where f of x is my density function. This generalizes to any function of x. Okay, so if g now is some function of x, it could be x squared, it could be x cubed, it could be x minus 2, whatever you want it to be, right? If you want to know what the expectation of a function of x is, where x comes from a probability distribution f of x, then that is defined as the integral across x of the function multiplied by the density function, okay? So the mean that we looked at is a special case where g of x equals x, okay? So this a thing is called the law of the unconscious statistician. It's called that because most times when we teach it in statistics, we treat it as if it is a definition. Technically, it's not a definition. It's a derived quantity that comes from probability distribution, probability theory. But anyway, it doesn't really matter. The key point is that we can write any integral like this, we can estimate in exactly the same way, okay? Where we take a large number of random samples from our distribution f, and then we can take the sample mean of g of x, yeah? So we take each of those samples, we apply our function, and then we average them, all right? And the reason why this is important is because it means that you're not limited to just taking, you can do essentially generate estimates of expected values of any function of a random variable using Monte Carlo estimation, and it will still be unbiased and consistent, okay? And I will return to this at the end. So why am I going on about this? Well, let's think about how we might calculate the posterior mean for a parameter theta, okay? So I have a Bayesian model, I have a single parameter theta. My posterior distribution is proportional to my likelihood times my prior. And what I'm interested in is getting that point estimate of the mean of that distribution. So what I'm interested in estimating is the expected value of theta. And using our definition, this is the integral over all possible values of theta times the density, the posterior density function, okay? Integrated with respect to theta. All right? So if I want to calculate this thing, and I don't know what f is, but I can sample from it, then what I can do is effectively estimate this quantity by taking a large number of random samples from my posterior distribution and then just taking their sample mean, right? And as long as I take a large enough number of samples, this is going to be a good estimate of the sample mean. As long as we can sample from the posterior distribution, right? And for any of you that know anything about random number generation, the classical way we generate random numbers requires us to be able to write down the density. The key problem with the posterior is because we do not know this normalizing constant, we can't write down the density. So the classic ways that we might sample from this type of distribution are just not very straightforward to do anymore. So the key thing is, how do I produce samples from the posterior, given that I can't specify the posterior completely? Okay. Oh, and I've just said all that. So, and so this is where we introduce the Markov chain component of this, okay? So what we are going to do, I'm going to go through this a little bit. But this is a reminder. So Andrew did cover this in the stochastic simulation lecture, okay? You've thought about a random Markov chain before. A Markov chain is simply a sequence of numbers where each number depends on where you are currently in the sequence, okay? So, for example, I could generate some value of x at some iteration I as a normally distributed random variable with a mean of the previous iteration with a variance of 1. Okay? So I take where I currently am and I add some noise. Okay? And then I move to that new sample. Okay? This is exactly an example of a Markov chain. It's known as Brownian motion, I believe. I often think about this as being like the drunken academic that comes from a pub, right? He wanders out and then wanders off in random directions, okay? If you run this type of Markov chain for a long period of time, it will just amble about all over the place, right? So it is a Markov chain because at each time only depends on where you are at the current time. This is called a first order Markov chain. It's not a very useful Markov chain, right? But it's just to bring in the idea that you're generating values based on, or updating sequences of values based on where you are, okay? Obviously, this is not very useful because this chain will just amble about all over the place. However, and this is the key thing, it is possible to generate Markov chains that don't just amble about all over the place. And in fact, we can generate Markov chains that will converge to a specific distribution. And in the Markov chain Monte Carlo literature, this is known as a stationary distribution. Okay? Now, there are lots and lots of Markov chains that have this property that it will converge to a distribution. But we're going to look at just one of those. And again, I don't want you to, you're not going to be coding this up yourselves, but I just want to talk you through to show you that it's quite a simple algorithm that has this property. And this is called the Metropolis-Hastings algorithm. Okay? More formally, it's called a random walk Metropolis-Hastings algorithm, okay? And this is what it looks like, okay? And it's quite simple, all right? So what we do, the thing we're interested in sampling is theta. So I'm going to use the subscript notation to tell me which iteration of my Markov chain I'm at. So I'm going to start at time point 0, and I'm going to choose an initial value for theta, right? And then I'm going to generate what we call a proposed value of theta by drawing from some distribution that depends on the previous value. Okay, so if I'm at time point 1, I will draw from some distribution that depends on the value of theta at time 0. Okay, so this is usually just some kind of stochastic noise. Okay, so in the previous example we had that normal distribution. You could just draw from a normal distribution here if you wanted to. Okay, we just add some noise. Now, in our Brownian motion example, you just automatically update to this point, right? You add some noise, you move, you add some noise, you move, and so on. In the Metropolis-Hastings algorithm, you don't automatically move, okay? What you introduce is you generate this value theta primed, and then you generate what's called an acceptance probability. And that acceptance probability is a function of the distribution you want to sample from, which is f, and the proposal distribution. So this is the probability distribution for moving from my proposed value back to the value that I had at the last iteration. And this is the probability distribution for moving from the previous value to the current value. Okay? So this is just a ratio of these two distributions. And then I have a ratio of the distribution I want to sample from at the proposed value and the distribution I want to sample from at the previous value. Okay? And these are just probability densities, so we know what they are, and we can write them down. Once we have this probability, then we take a random uniform 0, 1, and if u is less than alpha, we update. So we set the current value to be equal to the proposed value. If it's not, then we just leave the chain where it is. We don't move anywhere. Okay? And then we just iterate around this process over and over again. So the difference between this and the Brownian motion is we have this accept reject step here. So it is not guaranteed that this chain will move. Okay? It may move or it may not move. Okay? And whether it moves is done probabilistically depending on these ratios. And in the terminology, F is sometimes called the target distribution or the stationary distribution, and Q is known as a proposal distribution. So let's show you a very simple example of how this works. Let's say I want to sample from a normal distribution with a mean 10 and a standard deviation of 5. So I want to produce random samples from this distribution. So this is what my density function looks like for a normal distribution with a mean of 10 and a standard deviation of 5. And I'm just going to start my chain, say, at a value of 10. Let's start it at the mean. Okay? And then what I'm going to do is I'm going to use a uniform proposal distribution. So I'm going to take my current value and I'm going to add some uniform noise to that, right? In this case, I'm going to add somewhere between minus 15 and plus 15. Okay, so this is my current value, and then I take a random sample equally likely to be anywhere in this range. Yeah? Everyone happy? So this is my proposal distribution. And then I'm going to run through this algorithm, and I'm going to see what happens. Now, the first thing to notice, if it goes ahead, is that in this circumstance, where I have a uniform proposal distribution, then this is what we call a symmetric distribution, right? Because if I move from here to here, the density of moving from here to here is the same as moving from here to here, okay, because it's uniform. And in that case, that means that this thing and this thing are the same, and they cancel out, all right? So, and this will also work if you have a normal distribution, because a normal distribution is also symmetric. So anytime you have a symmetric proposal distribution, you can just add some noise. These things cancel out. So in fact, in this circumstance, this acceptance probability is the ratio of a normal distribution at theta primed divided by the normal density at the previous time point, okay? And then I just run through this process. Now, of course, you know, there are other ways of sampling from normal distributions, but this is just to show you that this works, okay? So this is what I've done. I've run this algorithm for 1,000 iterations, okay? And what you can see is that sometimes the chain moves around, it moves up, it moves down. Occasionally you see these flat areas where it hasn't moved and then it shifts, okay? So the Markov chain kind of iterates around. But in contrast to the Brownian motion example, it's not iterating around everywhere, right? If you look at this, it is producing values in the same region, okay? And in fact, if I take those 1,000 random samples and I plot a histogram, I get this. And if I overlay my true Gaussian distribution on top of this, okay, which is the red line, hopefully you can see that it's not too far removed, right? So these samples that I'm generating from my Markov chain, they are not, there's a technicality, they are not independent random samples because the value at one point depends on the previous value, but that doesn't matter as long as I have enough samples, okay? And so even with 1,000 samples, if I take my 1,000 samples that I've got and I take their sample mean, I get an estimate of 10.15, which is pretty close to the true estimate, the true value, which is 10, okay? And this will get closer and closer to 10 the more samples I take. I've only taken 1,000 samples here, but if I took 1,000,000 samples, this would be really close to 10, okay? This is the essence of how this algorithm works. And notice at this point, the only thing I'm sampling is this noise distribution, all right? I'm not sampling directly from F, I'm sampling from Q, which is just some noise. So it could be uniform, which is easy to sample from, or it could be some other distribution that is easy to sample from. And again, once I've got these samples, I can also derive credible intervals and all sorts of other things from this, because I have random samples. Now, the beauty of MCMC is that it actually doesn't matter even where we start the chain from. So this is exactly the same algorithm, but now I've started it at minus 500, which is miles away from a normal distribution with a mean of 10, right? And look what happens to the chain. It iterates around, but it starts to go, no, I want to go here, 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 and then it hits the right region, and then it starts iterating around in this region, yeah? So this, the reason why MCMC or Markov chain Monte Carlo is so powerful is because, at least in theory, these chains will always converge to the stationary distribution as long as you run them from long enough, even if you don't know where to start them from, okay? Now, of course, there is a little bit of a disconnect between theory and practice. So for some models, it can be very, very hard to get convergence, but certainly for a lot of fairly standard models, most of the software packages have very clever ways and will basically do this automatically. Okay? The key thing I want to point out here, though, is that there is this period at the beginning that we call the burn-in. Okay? And when you are in the burn-in period, these are not random samples from your normal distribution. Okay? So when we say the chain converges, we have to wait until the chain has hit the stationary distribution before we can start taking random samples, okay? Because these are clearly not random samples from a normal distribution, okay? So when we run MCMC, one of the things we do is we run it for a long number of iterations, and then we have a look at these plots, which are called trace plots, and then we throw away this stuff at the beginning, all right? We get rid of it because they are not random samples, because at this point, the Markov chain has not converged to the true distribution, okay? So if we discard the burn-in here and I throw the first 100 iterations away, then I get my nice random samples. Okay? Everyone happy with that as an idea, at least? Yeah. So this is all we're going to do, is use this algorithm or variations of this algorithm to do this sampling. Okay? So then the question is, oh, sorry, hang on, before I get onto that. Now, a couple of things to bear in mind when you're doing this is, if you use standard software, so if you want to fit generalized linear models or something like this, there's lots of software that will do it. You do not really have to know how the MCMC works underneath the hood. The software packages are usually clever enough to figure that out. What you do have to do, though, is you do have to examine these trace plots and check that the model has converged. Okay? So this is very important. If I don't check these plots, let's say, for example, here, that I ran 400 iterations, or let's say 200 iterations, and then I just take the sample mean of those 200 iterations, I'm going to get a rubbish estimate, right? Because at this point, the chain hasn't converged, right? So when you're using MCMC, you do have to manually assess these plots. Okay, and make decisions about where you throw this stuff away. Okay, that's very important. The other thing you also need to look at is something called the mixing. And that is basically how efficiently the chain moves around the space. Okay, now, in terms of assessing convergence, there is not an absolute gold standard. You push a button and you get a test for convergence and everything is fine. Okay, there are disagreements in the literature about how best to do this. There is also no guarantee that the MCMC will converge in a finite number of iterations. Okay? It is guaranteed to converge if you run it for an infinite number of iterations, but obviously we can't do that because we have lives to live. So, so there is an idea of how do you practically assess convergence? And one way that you can do it, and the way that I like to do it, is to actually run multiple chains and use multiple chains from different starting points, and then follow them on for long enough and see where they converge to each other. So in this example here, I've run 2 chains. It's a bit more easy to see on the gamma, okay? So this is for our SIR model. And here, I had one chain where I started gamma quite high, one chain where I started gamma quite low. And you can see that over time, they both end up in the same place, okay? So running 2 chains from multiple places can be quite a useful diagnostic check, okay? Where this can sometimes be problematic is if you have a multimodal distribution, because then you can end up with chains converging into one mode or the other. And if you do have multimodal distributions, MCMC is not the best sampling algorithm in that circumstances, but most of the time, hopefully, you won't fall into that. So once we've assessed convergence, we should also assess something called mixing. And mixing is basically just how efficiently the chain is moving around the place. So if I take our beta and gamma example, I've now run for 50,000 iterations. I'm going to throw out arbitrarily somewhere here. I think I throw out the first 10,000 iterations, and then I just perform my inference on the basis of the remaining 40,000. What you can see here, and this is what you're looking for, is that these chains are giving you fairly solid blocks of color. Okay, when you visualize them. And what this means is that the chains are doing quite a good job of moving around the density, okay? So in a perfect world, we would just move around the density independently, generate random samples. But here, because we've got this autocorrelated process, you can sometimes get situations where you don't get this nice block of color, okay? And if you don't get that, then that's a sign that something in your Markov chain sampler is wrong. So in particular, with a Metropolis-Hastings algorithm, the key thing is this proposal distribution, okay? And what's most important is how much noise you add, right? So if I add a huge amount of noise, right? If I'm here and I add a massive amount of noise, then it's very likely that the proposed value is far away from the distribution and it always gets rejected, okay? Because I'm basically not producing any samples that are close to the distribution I'm interested in. Similarly, if the proposal variance is too small, then I just make very tiny steps, okay? And then it takes me a very long time. So in this circumstance, the proposal variance is too small. And so what you can see is I make very, very tiny steps. But if my distribution is distributed like this, then to get from one side of the distribution to the other takes a lot of steps, right? So when things are small, you get this pattern. And you can see that this doesn't look like a solid block of color anymore, right? Similarly, if my proposal variance is too big, then I spend long periods of the chain not moving anywhere. And then I jump somewhere, and then I spend a long time. So again, that's not very efficient. Either of these two extremes mean that your chain is not really working very well, okay? Again, this is completely irrelevant if I could run it for an infinite amount of time, because it will converge and mix across an infinite number of samples, but in practice, I can't. So there is an element to Bayesian stats, particularly if you're using MCMC, where you need to look at these things and try and decide, have I run the chain for long enough? Do I need to play around with these samplers? And so on, okay? But these are examples of where I have poor mixing. And this is also an example of why you should plug your laptop in. Sorry, chat amongst yourselves for a second while I plug my laptop in. What's the passcode? Okay, sorry guys, we're back. Sorry about that, I underestimated the amount of battery I had. Okay, so when we're running our MCMC, we do have to sort of just be a bit careful about monitoring these things. Most of the software packages that you would use produce plots like this automatically, so you can generally get at them. A lot of them also, particularly the more recent packages, so ones like Stan and Nimble and those sorts of things, also have semi-automatic ways of tuning this variance for you, right? So often you don't have to really worry about it. It will tend to figure out what's optimal and it will tend to work. But these are just signs that something could be slightly amiss. And sometimes it's a case that you just need to run your chain for longer. And if your chain is very fast, then it just runs quite quickly. You can just run it for longer and it's all fine, and it'll eventually look like this. But in other circumstances, you might have to play around with this a little bit. And that obviously requires a little bit more insight into how the samplers work and stuff. But just to make you aware that these are the sorts of things that you have to look out for. So if we have poor mixing, that means that firstly, the chain takes a long time to explore the posterior, and it also might mean that it takes a longer to converge, okay, because it's not moving well enough. Optimizing MCMC is hard. There's a lot of theory, there's a lot of work going into this, but there are fairly reasonable adaptive proposal distributions that work very well, or alternative MCMC algorithms like Hamiltonian Monte Carlo will do all of this for you. Okay, so in essence, what you're looking for is something that looks like this. Okay, a solid block of color where it's not moving around. You know, if you're seeing a diagonal line, it's still converging, so it needs to be looking like this. Okay, cool. Is everyone happy, at least? Yeah? All right. As happy as you can be when talking about MCMC. Right, so, why, oh, sorry, yes?
So I was going to ask, how do you describe the package of the MCMC that hasn't converged yet from your estimates that you're trying to do?
Yeah, so what you do is you plot out these plots like this to begin with, and then there's usually a function in the software package that says, do you want to discard? Do you want to thin your samples? And so what you can effectively do is say, so what I did here was basically say, just throw away the first 10,000 samples and leave me with the rest. Yeah? But there is not an absolute goal. There's not like a thing that says, you know, a perfect diagnostic that says your chain has converged, right? That's just a choice you have to make, but usually it's fairly obvious. Like in this, it's pretty obvious that by about here, I mean, I could have even gone down to here. Like, it's fairly obvious this has converged at this point. But what you will sometimes see is this kind of thing where, at this point, because of the magnitude, because I started this far away, it's quite difficult for me to judge the mixing here. But what I would do in this circumstance would look at both of these and say, okay, well, if I throw away the first 10,000 and then I replot it, it changes the scale then, and that's essentially what I get here, right? So sometimes you can't see the scale, and that's an indication that you need to throw away some stuff. Yeah, is that? Yeah, but there are functions that do that for you. I mean, you can do this by hand. So these algorithms are basically throwing out a matrix where you have parameters as columns and iterations on the rows. So you can just literally, if you've got it as a matrix, you can throw away, just subset it and ignore the first 1,000 or something. Okay, so all of this effort, why is it helpful to us? Okay, why do we bother to do this for posterior distributions? Well, if you'll notice, okay, what we are trying to estimate, the target distribution, right? So the whole idea of this is what we are going to do is set up a Markov chain where the target distribution is the posterior, right? That way, the Markov chain can produce random samples from the posterior, and if we've got random samples from the posterior, then we can use Monte Carlo estimation to estimate the distribution, okay? And what is the problem? The problem is this normalizing constant, right? We know the likelihood, we know the prior, we can't calculate this. Okay, this is the thing that causes us the headache. However, in our Markov chain, in our Metropolis-Hastings algorithm, that acceptance probability, if you notice, is a function of the ratio of the posterior at the proposed value divided by the posterior at the current value. Okay? And using Bayes' theorem, we can rewrite the posterior density as this. And what you should notice is that there is an innocuous f of y on both the numerator and the denominator, which cancel out, right? So because this acceptance probability is a ratio, these two things cancel out. So the thing that I can't calculate, I don't need to calculate if I use this algorithm anymore, right? And in fact, my acceptance probability reduces to the likelihoods and the priors, which I do know, and the proposal distributions, which I also know, okay? So this is the thing. This algorithm was really the first algorithm that really opened up Bayesian statistics and made it generalizable. Because now we have a general purpose way of generating random samples from a posterior distribution, even though we can't calculate this normalizing constant. And this is, in fact, what we do. Okay, so in those examples that I showed you last time and the examples of the, from the SIR model, this is all we do. We run this algorithm, and we generate a large number of random samples of the parameters, and then we plot them out, and we get estimates for our posterior samples, right? If I take all my beta samples and I calculate the sample mean, then that gives me a point estimate of beta for beta, and I do the same for gamma and so on, okay? So that's really, really nice. Okay, so that's basically how this operates. But the other really nice thing is that quite often we might want to generate posterior samples for functions of the parameters, not just the parameters themselves. So an example in this SIR model is, let's say that I want to generate an estimate for R0, okay? R0 is not a parameter in my model. My parameters are beta and gamma, okay? So how do I do inference on R0? How, you know, it's a difficult thing to do, right? And in a maximum likelihood setting, sure, you can get a point estimate for R0, but generating uncertainty is quite difficult because you have to rely on central limit theorems, and maybe that doesn't work if you take ratios of things, okay? So there are kind of technical difficulties. In a Bayesian model, we can use the law of the unconscious statistician, right? So when I gave you that earlier and I said that this idea applies to functions of things, if I take something like R0, R0 is a function of beta and gamma, okay? This is a density-dependent model, so we've got the n in there, but we know the n as well, right? But essentially, for any random sample for beta and gamma, if I calculate beta n over gamma, then I have a random sample from the posterior distribution of R0, even if R0 is not a parameter in my model, okay? Because R0 is a function of parameters in my model. So if I take my 10,000 random samples or 40,000 random samples of beta and gamma, and for each one of those, I calculate beta over gamma times n, then I get a random sample for R0. So now I have 40,000 random samples for R0, and then I can plot a posterior distribution for R0. Right? And then I can do things like calculate the mean and the credible interval. So here, a point estimate for R0 would be 1.3. 95% credible interval. So there's a 95% probability that the true value of R0 is somewhere between 0.89 and 1.8. Okay? So it bounds 1. Okay? But I can also ask other types of questions that you can't ask in a classical framework. So for example, if I look at my distribution here, I can't usually generate a p-value from this. but I can do something different and possibly better, depending on what your viewpoint is. I can ask the question, what is the probability that R0 is bigger than 1? Okay, and if I'm making a decision, maybe I care about whether R0 is bigger than 1. The mean is bigger than 1, but I'd argue that there is a big difference between a mean being bigger than 1 with huge uncertainty and a mean being bigger than 1 with small uncertainty. And if I have this distribution, what I can basically do is calculate the area under this curve from 1 up to infinity. And all that corresponds to here is I take my 40,000 samples and I generate what proportion of those 40,000 samples are bigger than 1. Okay? And that gives me an estimate of the probability that R0 is bigger than 1. And that's exactly the same idea as you're using for these credible intervals. Okay? So it's the Bayesian context, you can think about things in a slightly different way. We wouldn't generally think about statistical significance and p-values. There is something called posterior predictive p-values, but that's mostly for model checking. But you've got this distribution and you can look at it in all sorts of different ways. Notice also that this distribution of R0 is not symmetric. This credible interval is not symmetric. Again, doesn't matter because it comes out of the model. This is a asymmetric distribution and you automatically capture that. Okay? So you don't have to make any central limit theorem approximations and things when you generate confidence intervals. This all falls out of the model. Okay? This is why I really like this. Okay? As long as you are prepared to go through the pain of fitting the model in the first place. Now, sorry, is there a question? Yes?
So in that case, you're making it like a beta and R, the gamma and the beta are known when you're generating the posterior for the previous slide.
For this one? Is it going to work or am I too far away? Yeah, this one. So here they're not known, they're estimated, right? So we have random samples for beta and gamma. And then so for each of those random samples, we can treat them as being known and we can generate the R0, okay? But the key thing is that distribution on the right is generated from 10,000 random samples from that distribution for R0, okay? And then if we average, I think it's 40,000 samples, if we average those, we get 1.3. Does that make sense? Yeah. Cool.
So,
yeah.
So the probability that you're talking about of R not being more than 1,
yeah.
Or maybe perhaps even less than 1.
Yeah.
We said we should be able to calculate the area under the curve.
Yep.
So how are we going to do that here?
So the way that you do it here is because that curve, that's not an analytical curve. That curve is just a density, a histogram, if you like, or a kernel density function of the samples. So empirically, what you can do in this case is you can take your 40,000 samples for R0 and you can say what proportion of those are bigger than 1.
Right. Okay.
Yeah? Or what proportion of them are less than 1 would also give you the you can also define regions. So when we're defining credible interval, what we're basically doing is defining a region in the middle where 95% of the samples lie. So all of these things are empirically estimated without you having to do a complex integral. That's the idea. Yeah. This is not a mixture model. No. This is...
Because I'm seeing it as beta. Another example of a mixture. Or can it be called that?
So this is, well, the beta and gamma are from the transmission model, right? So it's the transmission rate over the recovery rate. Do you mean a mixture model as in like a mixture of distributions? Yeah, no, this is deriving a single distribution from two other distributions. So it's not, you're not averaging the two distributions, you're taking a ratio of two distributions in this case. But that's quite a hard thing to do analytically, but we can do it through Monte Carlo estimation by taking random sample for beta, random sample for gamma, and then taking the ratio. And that gives us a random sample from R0.
And then it gives you this plot.
And that's what this plot is. Yeah.
And one last thing.
Yeah.
Validating this model, can you use the AIC?
So we would, you can do AIC if you take a point estimate. So if you were to take the posterior means of everything, you could possibly use AIC. So Bayesian model comparison is more difficult. There are other methods. There's things like Bayes factors and posterior predictive model weights and stuff. There are others as well, Isaac, right?
Deviancy mission criteria.
Yeah.
Watanabe generalization of the DIC. So there's no AIC here.
Yeah.
AIC is for the frequency side.
Yeah.
It's
But-
the area of DIC, the generalization of DIC is total complex is the WAIC, which is Watanabe AIC.
Yeah, WAIC is the best one. So DIC was used for a number of years, but it has some problems with certain types of models. But the WAIC is it's effectively a measure of predictive accuracy, and you can use that to compare between models. Again, quite a lot of software. I think both Nimble and Stan both will produce estimates of WAIC if that's what you want as well. Now, this idea of carrying these uncertainties and these samples through also carries through to what we call posterior predictive distributions. So let's say, for example, that I wanted to estimate the value of a new individual, Y star, given the data that I have. So Y star here is not data. This is maybe so if I was doing regression, this might be a new individual and I want to predict their outcome or something like that. Or it could be a forecast or something. Mathematically, we can define what's called the posterior predictive distribution as the integral over the posterior distribution of my model. So remember, my model depends on the parameters, okay? And so if rather than fixing the parameters to be a specific value, instead, I can produce a weighted average over the posterior distribution, and that integrates out the uncertainty in the thetas, okay? Now again, we don't do this analytically. Notice that this is an expectation, right? Based on our definition of expectations, this is an expectation over theta of a function of theta multiplied by a density, right? So if we want to make forecasts or predictions or whatever else, we can use Monte Carlo integration in the same way because our MCMC gives us random samples from the posterior, okay? And then we can do, usually, if this was a simulation model, I might run a simulation with those parameters and get some outputs. And then I just repeat that over and over again. And then I get a whole bunch of simulations, okay? And then I can plot those out in the usual kind of way, okay? So I can use this for doing model checking. I can use this for doing forecasting. I can use it. And the key thing is here, from an uncertainty perspective, Bayesians will harp on about this all the time. But I would argue that this is a better method than fixing the value of the parameter and ignoring the uncertainty. So if I do a forecast into the future, if I fix the parameter, I get some uncertainty, but that uncertainty doesn't represent the uncertainty in my parameter estimate. It just represents the uncertainty in my model. Okay? Whereas this allows us to also incorporate the uncertainty in the parameters, and this is a sort of natural thing to do. Okay, last couple of slides you'll be pleased to know. So we haven't talked about how you do this really for SIR type models. We'll do that tomorrow. But this is a really general purpose tool that you can use for fitting all sorts of different models. There are a bunch of software packages. The OG, I think, in my son's lingo is WinBugs, okay? So this was one of the first packages really to make. So what this allows you to do is they allow you to write whatever model you like within Region, okay? And then it will compile and do all the MCMC for you, okay? That being said, when I say any model you like, this is usually restricted to generalized linear models, so regression models. You can't really do the epidemic models that we're talking about here, but you can do the catalytic models, anything you can write down a likelihood function for in a relatively straightforward way. You can use these. So WinBugs is good, but it's not being developed anymore, but it is freely available. JAGS is an R-only version of this. There's also OpenBugs, which is an open source version of this. We'll be using one called MCMC Pack, but that's not one I would use very regularly. It's easy for us to reuse code for the practical. The two that I would recommend if you wanted to do Bayesian analysis in more detail are Nimble and Stan. Okay, these are both really good packages. This is an R package. This has an R version if you want it, but it also has a Python version and various other things. These two are being actively developed. They've got a lot of functionality. They fit all sorts of models. You can fit spatial models. You can fit, autoregressive models. There's all sorts of stuff you can do. There's also a couple of, in R in particular, there's a couple of packages, BRMS and RStanArm, which simplify this down even more. So if you just want to do regression, RStanArm will just allow you to write a very simple regression function, set some priors, and it will run everything in Stan in the background and just throw the results back. So if you're just doing simple regression and you want to play around with this, these are really good. Okay? And the idea is that what they're trying to do is move towards a situation where fitting a Bayesian model is no more complicated than fitting a maximum likelihood model. Okay? Probably not there yet, but also these packages allow you to fit any model and not just the ones that are coded in. So these are really good. I think that's the last slide. Yeah, so first practical, which we probably won't get very much done now because we're running a bit late, is to fit the catalytic model that John introduced earlier. And there is some code in there to do this both from a maximum likelihood perspective using the optim function and also using MCMC-Pack to do this in a Bayesian analysis. Okay, so hopefully it will just give you a feel for how you can implement these things in a sort of general way. And then tomorrow, the final two lectures will be introducing something called particle MCMC with a practical, and that is a way of being able to fit these really more challenging infectious disease models, so things that are not regression, effectively. So we're going to look at that in more detail tomorrow. Okay. Thank you very much. Does anyone have any questions? No? Okay. So yeah, feel free to start the practical, the catalytic model practical. I know we've got dinner at 6. So
realistically, we'll make a decision about.
oh yeah, so don't start it because it's 10 to 6.